and also one-time password generation, which we don't talk about in these particular devices, but other authentication tokens like Secure ID, CryptoCard, and Secure Computing SafeWord products are all authentication tokens that are one-time password generation products. And on my website, there's some discussion about some weaknesses in those as well. But what we're looking at here is really physical hardware-based stuff and what we can do to bypass these things. So what we're going to look at first, as I mentioned, is USB tokens. One is the Aladdin systems. It's the eToken 3.3.3.x. And the reason it's that is I originally was given this device, and it was called the eToken R1. After we released the advisory on this device, Aladdin came to me and said, no, that was our prototype version, 3.3.3.x. Same thing goes with the Rainbow iKey. It was the 1000. Oh, no, sorry. This was the eToken R1, but then they told me that it was this. With the Rainbow Technologies key, the 1000, when we released the security advisory, they also said it was a prototype. So take that with a grain of salt, if you believe it or not. Whatever it is, I had these devices with no knowledge that they were prototype devices. I was given them from salespeople trying to demonstrate their product, so I assumed that they were production devices. And this research was performed in May through July of 2000, so a little while ago, but it still is interesting to see some of these problems and how they're still similar today. So I should say that new versions of both of these products do exist. They do have the iKey 2000, eToken R2, and eToken Pro, and a bunch of other varieties. There's also a few other vendors out there now that are competing with these guys. So what we're going to look at for the USB stuff is analyzing three areas. First, we're going to look at mechanical stuff, so physical access to the keys. How could we access the circuitry, if any? Then electrical stuff, what we can do at a circuit board level. And then look at any software and firmware attacks. And for those who were in my Introduction to Embedded Security talk earlier, you'll notice that these are the three sections that we were talking about protecting, is mechanical, electrical, and then firmware. So obviously, from an attack point of view, you want to do the same thing. So as far as the enclosure and the housing goes for the USB tokens, the goal, as I mentioned, is to get access to the internal circuitry so we can see what sort of attacks we can launch on that. The main goal is really to succeed without having any visible evidence of tampering, because most of these people have on them at all times, so, or at least they'll leave them at their desk or whatever for a coffee break, and that's when an attack can take place. So you don't want it to be obvious that somebody had tampered with the device. It turns out for both of the devices that we talk about, both of them can be opened without any visible evidence of tampering at all, and we can do it with just standard tools, X-Acto knife or screwdriver or whatever. So really easy. Fingernail, I guess, if you have strong enough fingernails, as you'll see. So you really don't need any tools. It's a piece of cake to open. And so for the eToken, which I guess is this one. I mean, you guys probably can't tell the difference anyway. This was moderate to open, and you'll see why. Once you get inside, though, there's no protection of circuitry at all. For the iKey, it was easier to open, but once you get inside, you have some epoxy to deal with, and it's moderately more complicated, except if you were in my other talk, you'd know why, and I'll show you why it doesn't really matter in this case. So for the Aladdin, this was the one that was moderately hard to open. It turns out they have a two-piece housing to protect the circuitry, and there's just glue around the housing. So the glue can be softened with a heat gun. Just briefly heat the unit, slit one side with an X-Acto knife or your fingernail, and then you can open it up. As you see, these are the steps, just heating it up, using the X-Acto knife and pulling the circuitry right out. Basically, like now I have the clam shell of the case, and when I'm done, I can just reseal the housing and put everything back together. It does require a little bit of care, though, because if you are using a knife and you slip, then it's going to be obvious all of a sudden that you've tampered with the device, and whoever owns it might say, hey, look, someone messed with it. The good thing about authentication tokens from an attack point of view is that they usually get scuffed up when they're in people's pockets or thrown around with their keys and whatever. So it's usually not going to look as nice as a brand new one does. So if there's already scuff marks on it and the attacker does make a mistake, you might not notice. For the Rainbow iKey, it's a little bit different scenario where there was no glue at all, and it was still a two-piece housing that was basically held together by this little metal piece of the USB connector. So it was two plastic pieces and then the USB connector. No glue at all. You just use an X-Acto knife or just pry it open, and you're in, and you have access to the circuitry at that point. So under 30 seconds. So this could easily be a lunchtime type attack where you leave your keys or you leave your authentication token, you go get a cup of coffee, you go to lunch, an attacker can come by, read your information, clone the device, do whatever they need to do within 5 minutes, and you'd never know. So also if you use these things and you check your coat or whatever, the coat check example I always give a lot too, you have some attacker working the coat check, they have access to your keys and do whatever they need to do. So a little bit more on the iKey, just to see how the unit is put together, is basically socket and post on both sides, and that's why they didn't use glue. On the top side you can see little holes here, and on the bottom side you have the corresponding posts. So it just plugs right in together, and then the metal housing of the USB clamps the two together at this point. These are the 4 connectors for the USB connection there. So that's all it is that's keeping it together. Recommendations if you are designing these things, or if you happen to have them already deployed and you might want to try to retrofit it. One of the recommendations is to have a design that prevents the units from being easily opened, obviously, which sometimes is easier said than done. But using a sealed or a molded housing in some case, either with ultrasonic welding or high temperature glue, will make it a lot harder for somebody to get into. And if they did, it would probably be pretty obvious that something has happened. And we'll show an example of this later on, of one authentication token that Jeff Moss sent me right before the talk. That was sealed. It was a one-piece unit sealed ultrasonically. So in order to get into it, it wasn't as easy as just taking an X-Acto knife on it. So if you use something like that, it will be a lot more obvious that an attack has taken place, and if done properly, it will require complete destruction of the physical housing in order to get access to the circuitry. So in most instances, the attack would not be feasible. Using high temperature glue, as you saw with the Aladdin device, they did use a glue, but it was a low temperature, so it melted when I was using the heat gun. So what I recommend is using a high temperature glue that the plastic of the housing will melt before the glue does. So that way the housing will deform and it will be obvious that something has gone wrong there, somebody's tampered with it. So another thing, obviously, if you're designing these or using them, consider the service issues that if a legitimate user can open the device, which you'd want from a manufacturing point of view to make it easier for debugging, so can an attacker. And then if an attacker can get access to the board, then you might have some other problems. Another suggestion is using some tamper mechanisms, or rather anti-tamper mechanisms. I discussed these in my previous talk, and there are some notes in the proceedings about it. Most of the time using an epoxy encapsulate of some sort of glue over critical components to protect those components from being probed and to prevent an attacker from easily getting access to it. And we'll show a picture of that too. And then obfuscating part numbers from the actual parts on the board. So if the attacker does get access to the unit, it will make it a lot harder for them to reverse engineer the design and figure out what's going on. And in both of these cases, as you'll see, it took about 20 minutes each to put together a full schematic of the design, and then I could figure out exactly what was going on at that point. And that's actually in this section. So once somebody has access to the circuitry is where the real attacks go on. We can now reverse engineer the design, at least get a system level diagram of it, say, okay, look for attack points and see where the best places are to attack it. In this place, for both products, there was a similar design, and it led to the same vector of attack, which was reading from unsecure external memory, which ends up being serial EEPROM devices, which use 2 or 3 wires, serial wires, to read and write data to. So there's no protection at all. And those devices can be read in circuit, so you don't even need to remove the device from the board, and you can use either a standard device programmer or put something together yourself for $5 or $10 worth of parts. You just read it through the parallel port. So in both cases, both devices used weak encoding algorithms to protect the pins, and the pins vary for each product, and we'll get into that. So for the Aladdin device, once we open it up, this is a picture of the board inside, and you see there's part numbers still on stuff. This one there is, it's just hard to see. This is the processor here, it's a Cypress part, and back in 2000, there were only 2 or 3 vendors that actually had processors that supported USB at that point, and Cypress was one of them. And this was a Cypress like 7C63000 series or something. So it was easy to go to the Cypress website, and they were touting their processor as a general purpose processor that had USB support. So all the data sheets were there. I could figure out exactly how that was interfacing. to the serial double EEPROM, to the clock circuitry, and to the power supervisor that's on there too. So it didn't take much, and there's not a lot of parts in there, so you could see how easy it is to do. And we ended up with a schematic like this, which is hard to see, but basically the blocks are here. We have the processor, the USB connection, little status LED, the processor, and then the serial double EEPROM. So I could figure out right from here, okay, chip select is connected, the clock, the data in, and the data out. So I knew right away how this was connected, and then I could look at this and say, okay, I'm going right for the memory. Even though the Cypress device has its firmware stored internally to the device, and it did have its boot block, or it had its security fuse set to prevent easy access, and I think we discussed that, to prevent somebody from reading the firmware out of it, but it didn't matter in this case because I could just access the serial double EEPROM. So this is the memory map of the double EEPROM that I obtained from reading the double EEPROM from the device, and then going back, plugging the device into the PC, changing some contents, changing the password, plugging it back in, seeing what changed, and then I figured out where the user pin is, where the administrator pin is, and where the default pin is, and then some of the other information that's standard on an authentication token, which was the FAT file system stuff, where the data is, and where the public data is. So everything's there, and with that I could obviously say, okay, I'm going to address 20 and I'm going to read that, and we'll show that in a second. All right, so for the Aladdin token, there's two pins associated with each device. One is the user pin, and the user access has complete control of like the e-token file system. So that's what most users would have. And then you have administrator access, which is used for the administrator to initialize the key before they deploy it to everybody. So for the most part, administrator access will reinitialize it, but they don't have access to the private data. The user key does. So let's see. What we did is, let me remember what we did. This is the dump of the memory area. So as I mentioned before, we changed the passwords and we could view how they were changed. So this was the first memory dump, and we knew that this wasn't just a direct representation of our password. It's encoded in some form. And also I should mention too, the Aladdin devices, this is how we figured it out. The Aladdin devices have a default password that is, I want to say it's shipped with the device. And we entered that default password in, and this is what we got for the encoding. And the default password actually turns out to be, and they mention this in the documentation, it's 8 bytes of FF, which is a non-printable character. So that's just how they initialize it, and that's how it's configured. So we just set it back to FF, and then this is the representation of that password. And we can see that the user pin is now set to the default pin. And this is the default pin down here, which corresponds to FF. So now we know that somehow 8 bytes of FF corresponds to BE74503B hex, whatever. So now we just had to figure out a way to see how that was done. Actually, in this case, we didn't even bother, because it turns out that all we had to do, instead of figuring out what this representation of the user pin ended up being, we could just copy the default pin setting BE74503B into that setting. So we just totally ignored all of the crypto routines there. Sorry, took me a while to remember exactly what we did. So all the attacker has to do in this case is get access to a device, connect to the double EEPROM, change that memory area of the user pin, which is located at 10 hex, change this back to this default pin string. And I should mention that this default pin string changes per device. So it's not always BE74503B whatever, but we know that this location here is always the default pin string, which always corresponds to 8 bytes of FF. So all we have to do is copy that string into the user pin string like we have here, and then we can log into the device as user with 8 bytes of FF. And that's what we did. And that's what we can show here. So, oh no, actually, we can't show that here because of this. So this program I wrote, it's a proof of concept tool called Heimlich, and it's up on the website. What it does is it will search the USB ports for the e-token, so your modified e-token. It will retrieve the configuration data from the key, log in as user with all Fs, and then retrieve all the public and private data, which will essentially allow you to clone the token. And the tool will expect on the command line, or the tool expects that the user pin has already been reset to the default state, as I mentioned, with the device programmer. The problem is, and the reason I can't show you the demo, is the tool requires an old version of the SDK that was available on eToken's website, which was 1.0. Because this was an older device, after eToken found out about the problem and they had redone all their SDKs and everything, they stopped supporting this device. And since that point, I had changed jobs and changed computers and lost the initial install. So the new SDK is like 2.0, and it has all the newer devices except this one. So I'm pretty bummed about that. But the code is still available on the site and their source code. If you happen to have access to the SDK 1.0, you can run this and also send me mail if you do, and send me the SDK. So cool. Pyro thinks he has it, so that's good. And it's interesting to see. And since we couldn't actually run the tool, I just showed you a screenshot of it here. So what would happen is after you type Heimlich on the command line, it will say eToken found on slot 5, which is just one of the USB connections, basically. The token ID, which is supposed to be a unique ID. Now keep in mind that all of this stuff is stored in Flash, or in serial EEPROM, sorry, so it could be changed. So this unique ID isn't really unique because it can be changed. You have the token ID, version of the firmware, file system size, size of the data being used, secret, size of the secret, how much data is being used. So right there you can just see some general information. And this is even before we've logged into the device. At that point, it's going to try to log in with the default pin with that 8 bytes of FF and success. Then it basically just iterates through the entire file system and retrieves all of the files. So these are just the file names that it uses that are kind of token standards of 3F00, and then these files obviously I've made up myself. So it just retrieved all that information, stuck it in the directory, and it's there for us to either use at that point or load back into another device by just reprogramming the serial EEPROM there. So that was kind of interesting. And at that point too, I mean, the tool is one thing, right? I mean, you could have some useful data there, but also if you just reset the pin, then you could actually use the token to log into whatever services that they were using the authentication token for. So you don't necessarily need this tool to actually perform an attack. You just change that password back to the default pin, plug it in, and you can enter the default pin on Windows with like an Alt 0255, and then that's FF. So you can do it from the keyboard, and it lets you write in. Does that make sense? You guys totally confused now, or was that okay? Okay. Any questions? Okay. Now we'll get on to the other one, which hopefully I'll remember better. This was the iKey 1000, so this was the other device. And you see in this case they use some epoxy encapsulation on the boards, which was what I discussed, just some covering over it to prevent easy probing from somebody. And it's obvious in this case by looking at it that this is a processor and this is some sort of memory, just because if you do enough reverse engineering and you can identify parts, there's a crystal here and there's nothing else. So it's just kind of an educated guess. Also, what I ended up doing for the first unit I had was take this and take an X-Acto knife, scratch off the top of these, and the part numbers were right there for me so that I could pull up the data sheet and create the schematic, which in this case looks basically the same as the other device, give or take. It's the same processor, actually, that Aladdin used. They have another serial EEPROM here. It's a different brand. It's a little bit different the way that it interfaces, but it's still a serial EEPROM, and it still uses data out, or data in clock lines. And in this case, they have an external footprint, unpopulated footprint, for a memory upgrade. The device that we were looking at was an 8K device, but this board supports 16K. So I'd mentioned this in my other talk as well. In this case, even though they protect this area here of the serial EEPROM, because it's a serial EEPROM and you use your clock and data and ground line, that's all you need, they come out right to these pins here. So I don't even need access to this point. I can connect my device programmer to these leads, read the data right out of it. If they did happen to cover that, another thing I did do is just scrape off the edges of the epoxy here, get access to the pins, and just clip on with a dip clip type of thing connected to the device programmer and read it that way. So as you see, by doing I mean, this was easy enough to see just by looking at it, but by putting together a schematic, I could really identify that this was an external interface, using a multimeter to probe continuity between parts and know that these two were actually connected, and then you see here the data and clock lines. So right away, I knew that the unused footprint was exactly what I needed. So one thing I do say, if you're coming from a design point of view, understand what you're trying to protect and what areas you're trying to protect and why before you just go and add some epoxy, in this case, to the board, because it didn't serve any extra protection and probably cost them money. So for this attack, as I mentioned, you can either attach probes to the unpopulated footprint or to the pins of the device if you scratch off the epoxy. And also, there's also a unique serial number for these devices as well that's also stored in the EEPROM. It can be changed, removing the uniqueness. So if somebody, if some sort of authentication program or some sort of tool was basing it off a unique ID, sort of like some of the wireless access points are doing MAC filtering, even though you can change MAC addresses, it's the same type of thing. Somebody could easily just change the unique ID if it's looking for that. So for the iKey 1000, they have what's called a master key, the M key, which is the administrative password, similar to the Aladdin device. With the M key, it gives full access to the device this time, so this was the obvious target for our attack. It turns out that you can have up to 256 character ASCII, but I don't know anybody that's ever had a password that long. It's human nature to have a short length password, regardless of how much you actually get. In this case, they shipped with a default password of rainbow. And what we turned out is there was a hashed version of the M key stored at a particular address in the memory, and that was done the same way by changing passwords and seeing what changed in the EEPROM. In this case, it's MD5 hashed and then also encoded in some way. So rainbow MD5 hash was CD13 whatever, and then it's encoded in a way to D2 DD whatever, which we knew because that was in the EEPROM, but now we didn't know how it was encoded. And the way we found out that it was MD5, it was just kind of one of those things to check, because people just usually use MD5 and then say it's secure. So basically what happens with the M key password is you first have your value A, which is your hashed M key value, which is MD5 of rainbow. And then you have your obfuscated M key value in the EEPROM. So right now, these are our two known things. And we know that because, actually, I think in the documentation, they actually said that they MD5'd it as well. So these are our two knowns, so now we had to figure out how these corresponded back to rainbow. And it turns out just by setting, do I have an example of that here? Yeah. And we have a copy of it here. So we figured that out by setting the hashed M key value in the EEPROM to all zeros. And then that way we could say, okay, if the hashed M key value is all zeros, then the obfuscated value must be, comes out with this, 1F01 whatever. And then we just did some kind of pseudo cryptanalysis stuff to figure out that it's just a bunch of XORs and additions and stuff. So I mean, that took a few hours to figure out how the obfuscated version was converted from the hashed version. Okay, so in this case, it turns out that all the PC applications that communicate with the iKey device convert the ASCII password into its hashed M key locally before sending it to the key. So in that case, that the iKey API running on the PC side, on the authentication side, just requires the hashed M key and not the obfuscated M key, meaning you don't need to know the actual password to access the device, just the hash. So it turns out, in this case, we can get administrator access in two ways, both with the M key. One is to determine what the hashed M key value is based on the obfuscated M key stored in the EEPROM, which would just be reading the device. We know where the location is, XOR it, figure out the hashed M key that way. And at that point, it's just MD5, so we're not going to actually do a dictionary lookup against whatever password, even though we could do a dictionary lookup of hashes on MD5, but we don't need that because all we need is the hashed M key to get access. Or we could just encode a new M key using our own password string, MD5 it, encode it the same way, stick that into the EEPROM, and we've just written our own password into the device. So it depends on your flavor of attack. For the example demo, which does work, what we do, this one's called iSpy, and it will, same type of thing, you plug the USB key into your PC, and it will retrieve all the configuration data first. Then it will convert the obfuscated M key back into the hashed M key. So on the command line, you give it the obfuscated M key that you've read off of the serial EEPROM of the device. It will convert it back to the hashed M key, then log in as administrator using the hashed M key onto the device, and then just retrieve all the file stuff like we did before. So obviously still a proof of concept, but that's all that we needed was the hashed M key. So I'll give an example of that, even though this is what it looks like. So the example I want to show you, just because it's cooler looking than this, it will display all of the configuration information. And then on the command line, our obfuscated M key, then it creates the hashed M key and then logs in and dumps the file. So pretty cool. We're on iSpy. Yeah. Sorry, this screen's like, I wanted to get the font really big. All right, so we have our iKey 1000 devices here, which hopefully both of them are already programmed with the obfuscated M key that I read earlier because I don't have my device programmer here. So I'm just going to plug this in. And you can see on Windows it just said rainbow security token detected, and then it just disappears. So what I'm going to do, in this case, the hashed M key, or the obfuscated M key value in the device was, let me shrink this down. D2DD B960E0E. All right, let's see if that works. Okay, so what I did, so it's just exactly what you saw before. Ignore this header. I don't work there anymore. So it opened the device, retrieved all of the standard configuration information. This can all be done before you actually log in. Then it took the obfuscated M key, which I read from the serial EEPROM, and I typed on the command line, converted it to the actual M key, sent that to the device, gave me a successful master key verify, and then dumped the device here. So there's only 2 files on this one. If I take this out, the other key might have something. Oops, bad Windows. I guess I'm supposed to shut it down properly. So if I put the other device in, this one might have some more data on it. Yeah, so this has a few more files on it. You see it took a while because it was iterating through all the different files and directories and whatever, and came up with these other files. So those files are now stored in these directories, and we can just like go in and look at them. I don't know if there's, yeah, there's nothing in that one. Oops. Sorry about the swears. Yeah, so then there's, inside of that folder 0000, there's these other files here, and then there's going to be data in those of whatever sort. So that's the other proof of concept attack in this case.
You can read those files?
Yeah, you can read those files. I'll try to do it just with, nope. I can't remember how they're actually stored, but I mean, it's probably just binary data. Yeah, this one is probably just nulls. But yeah, if there was data stored there, like if someone had actually used these devices for something, there'd be data on there with credentials, private data, whatever they're using it for. You'll be able to read that with a hex editor or whatever in whatever file format it's stored. Because basically, all the USB token ends up being is a file store. It's just a file system with a password. So once you've retrieved the files, however they store that information, you can read and do whatever you want with. Or if you wanted to just clone the token, you can do that too. Well, the PGP key generation storage stuff as far as storing things on keys. Well, it all comes down to how they're stored on the key. If they were using one of these keys, it would be total crap because then you have access to their PGP keys, and then you do whatever you need to do. So it's really like what it comes down to is you can't have a secure product. You can't have any secure software without having a secure hardware base. So if somebody's using an insecure piece of hardware to store secure stuff, that just by default ends up not being secure either. So I would definitely, if you're using a device like this, I'd definitely try to attack it in-house and see if there's similar types of problems. Did they fix these issues? From what I know, they made it physically harder to access the device, access the circuitry, and then actually we look at this later is iKey also changed to using a different part, they say, like a smart card type of device, where then you could probably just attack it with more smart card related things. But yeah, I mean both of these companies, once they saw this, after they freaked out, went and fixed it, which was good. Okay, so recommendations as far as both of these attacks were pretty similar as far as they had their XORs against constant blocks, and they had their double EEPROM totally accessible. We could just read and write to that, set our own passwords, and get into both devices. Some recommendations that I had provided in my initial paper on this topic back in 2000 were some of these things, and it looks like both companies have actually implemented some of this stuff, is using microprocessors with internal memory, so keeping all of the data internal, at least will make it harder for somebody to just go and read the memory like we did. The only thing is there are still attacks against internal memory, die level attacks, which we don't talk a lot about here, but it's analyzing the silicon die to read data right out of it. And that's something, if you're here for DEF CON on Friday morning, I'm giving a talk on that, and the slides will also be up on my website if you don't make it. But it makes it a lot harder. That's more of an advanced attack. So also make the sensitive components more difficult to access. The processor, the RAM, whatever you're using, the ROM, make it a lot harder to access than just opening up the device and it's right there waiting for me. And then also cover the components in epoxy, as I mentioned. It's somewhat good. It's initially used for these sort of things, protecting from dust and high voltage arcing and stuff like that. And they weren't really intended for security purposes, so there are ways to get around them using solvents, using a Dremel tool with a wooden skewer as a bit is something that kind of takes it off pretty easily. So it adds a level of security there, but I wouldn't really depend on it. Another thing you could also do, and this is what some of the guys started to do with the new devices, is using non-standard or harder to probe package types. Chip on board is one where the silicon die is wire bonded directly to the board, and then ball grid array is another one where all of the pins of the device are underneath the device. They're not laid out on the plastic sides of the package, so all the balls are underneath, and they're a pain in the ass to probe without the correct tools. And then another thing vendors can do, remove identifiers from the devices, make it a little easier or a little harder for people to reverse engineer. The software stuff we talk about for the USB tokens is, I just wanted to mention it. It didn't really end up with anything. In this case, it was inconclusive, and since we already owned the devices and hardware, software is just kind of an afterthought to look at. But it is something to keep in mind that if you can't have access to the hardware, there might be other ways that you can attack it. In this case, I define software attacks as being non-invasive, no physical tampering. So this is what I'd try to look at if I had a sealed device that I didn't want to open. The two goals here for attacks would be to examine the communications between the USB device and the host computer using like USB Snoopy for Windows. There's probably some Linux and Mac-based tools. I don't know. I only use Windows, unfortunately. And then after snooping the communications, see if there's a possibility to brute force a password out of that. There are some other attack things, but these are the two that we looked at for these devices way back when. When you are monitoring the communication, trying to see if there's any undocumented commands or debug features that could be used to the attacker's advantage. Whether that's basically just seeing how the known commands are translated into byte level commands and then just creating new byte level commands and seeing what happens. See how the handling of intentionally bad packets is with some USB protocol analyzers, hardware-based devices that you can use to monitor communications, you can create illegal USB packets. So you can just send illegal type of data to the device and see how it handles it. For the most part, it will probably handle it because they're using a Cypress device that has this USB module on board. So the fault really would come down to Cypress. But either way, if the device handles USB improperly, it might retrieve some sort of data, or it might fail in some way that would be beneficial to an attacker. So the attack process in this case, at least in our case, of what we did is analyze the typical data transactions, either try to send commands outside of what we regularly see, or try to send illegally structured packets, and then monitor the data on the bus and see what it sends back, see if it like croaks and throws up some data for us. And then some of the tools that you could use, either hardware or software-based analyzers. Snoopy Pro I use a lot on Windows. Source USB is one that I just got a demo of, and there's a 30-day trial somewhere, so that's pretty good. And then some hardware-based devices, they're pretty cheap. The Cat-C is expensive, but then you have like a $100 device that you could buy to emulate some of the USB traffic. So if you wanted to get down to that level, you could.
Just out of curiosity,
Yes.
when you were originally monitoring USB bus, did you find any USB device that have a problem sending password requests through the USB bus itself?
When we were monitoring the USB bus, did we find any devices that were sending the password in clear over the USB bus? Not with these two devices, but it is highly likely that devices would do that. In my previous talk, and you might want to refer to the slides for the Introduction to Embedded Security talk, but some products do send things that they shouldn't send over interfaces, so either over RS-232 or over USB. And the example I have in that presentation was with the Palm OS devices that send an encoded version of their system password right over the wire. So you could sniff that, decode that password, and then you have access to their Palm device. So for these two devices, no. For other devices, yes. It's probably likely that they would do that. Did we test the 2000 version of the iKey? We have a slide on it, but we didn't do any serious heavy hitting like we did in this point. They sent a few years ago, and we just kind of blew it off. But you'll see a little bit. We didn't get down to any of the software level stuff with the iKey 2000. So this is a screenshot of using Snoopy Pro to just monitor the enumeration of the USB device on the port. In this case, we're just showing some of the standard descriptor class stuff for the device, but there's all sorts of packet data that we can monitor going back and forth and see how it's handling stuff. So that's an interesting way to do things. Now for the iKey 1000 specifically, we had an idea to perform this other sort of timing attack against the device to determine what the mkey value was. It turns out that, let me remember, I think for the user password for the iKey, they had for the user account, they had a counter that you'd only get like 3 or 10 password attempts before the device erased itself. However, for the mkey, there was an unlimited amount of attempts you could take for guessing the password. So that's why we went to try to see if we could brute force the password in some way. But obviously, brute forcing a 64-bit mkey value isn't feasible of an MD5 hash or whatever, especially back then, unless you're doing a distributed sort of attack or whatever, but we didn't really count that in. So instead of doing a brute force attack, we wanted to see if we could take advantage of how a compare function was done on an 8-bit processor. And we knew they were using an 8-bit processor because we knew it was a Cypress part, and we had the data sheet, and we could see all of the commands for the device and everything. So we knew exactly how things were working at that level. So we figured maybe we could get lucky on it since we're working with an 8-bit processor, but we're comparing a 64-bit input value with the mkey. Maybe we could do some sort of timing attack and hope that it would take a longer time for the USB device to respond back to the user if you had more matching bytes, and we have a picture of that on the next slide. It turns out that we couldn't do this because the driver latency, the USB driver, even if this thing was true, which it is, that on how a compare function works, if we had more bytes correct in our brute force, it would take a longer time. The driver latency just totally erases that because it's orders of magnitudes higher than the actual time that would be different in the compare function. So this is basically what I'm trying to say, is if we have our 8-byte value, which is our 64-bit, for each byte it's going to compare it The first byte will compare against the first byte of the M key value. If it's incorrect, the compare function is going to return right away. So right away we know, okay, that first byte's not right. So we could basically brute force through that first byte. If it takes longer than it did for the invalid entry, then we know we have a correct first byte. It will increment, compare the second byte together, check that. If it returns right away, we know it's wrong. If it takes longer, we know it's right. And that way we can kind of segment it a little bit. Question?
Why did the latency of the driver affect the accuracy of the snooper?
Why would the driver affect the accuracy of this?
Of the snooper? Did you measure latency of the snooper?
Could we measure latency of the snooper? Yes, we could, but in 2000, I don't think USB Snoopy was available, I think. I'm not sure if you could get to that level, but yeah, I mean, that would be a good thing to do is measure the time, and then you know the latency of the drivers, and then you could subtract that. And another thing that I kind of had an idea about is maybe, I don't know if Linux is any better as far as having a lower latency, or also making some sort of custom USB host where you know exactly what the timing is, you know, build a little hardware jig, emulate enough of the USB to do your compare, and then see what happens. That way you'll basically have exactly the time you need. 4 years ago, that wasn't something that we wanted or could do. Now, the availability of USB devices and USB controllers and everything is such that we could. So in this case, that sort of attack didn't really work for us, but it was something that we had planned and wanted to mention as a possibility. Recommendations for firmware on USB devices, and basically for any devices in general, is if you do have undocumented commands, get rid of those. Development routines, all of that stuff should only be for developers and not for end users. Protect against bad packets, because that's what attackers do, is try to break your functionality there. And then design each of your routines to make a constant amount of time. This is something that, with some timing attacks, Paul Kocher and some guys at Cryptography Research in San Francisco had done a bunch of timing attack work, kind of related to this. That basically one of the solutions is design all of your routines to take a constant amount of time. Then you can't identify which routines are crypto routines, which routines are standard operating stuff. So something to think about. So some of the newer token technologies we'll look at now to compare against some of the old ones that we looked at. We did do a quick evaluation of the iKey 2032, which is a 32K version of their iKey 2000, I guess, and then the Authentinex iKey, which I think I had picked up at some security trade show somewhere. We'll look at just some hypothesized attacks and weaknesses. In general, the devices we looked at are harder to open and to access the circuitry. It doesn't mean they're more secure. It just means that they're harder to open, and I personally didn't really do anything with them other than that. There is no known public research performed on any of these devices, which may or may not be good depending on which side you're on. So here's the iKey 2032, which is this one here. You guys can come up afterwards and kind of play around with these things. What they did in this case is it was still a two-piece plastic housing like the original iKey device was. In this case, though, they potted the device completely with epoxy encapsulate, basically just filled it totally full, which cracked on opening, meaning I just still used my X-Acto knife around the edge, came up with these two pieces. This is the top piece, and then this is the bottom. So I could see it was open fine, but then it's now this bottom part's totally covered in epoxy. So for a quick attack, it obviously wasn't going to happen. Turns out that the encapsulate softens with a heat gun. So I don't have any fun pictures of it, though. So it does soften with a heat gun, so you could take a heat gun and your Dremel tool with the wooden bit and kind of get at it. And the reason I use a wooden bit, other than the fact that it just seems to work, is that if you're using a metal bit and you're drilling through stuff, you could easily rip through traces, you could easily destroy devices and things like that. So the wooden bit doesn't seem to do that. It doesn't even remove solder mask from the board, which is cool. So with the 2032, once I played around a little bit with the epoxy, I can access all pins of the processor, which is like somewhere in there, which is a 24-pin SOIC, which is also what was used on the iKey device originally, except they had a different package type. It was still a 24-pin device. So I'd probed a few of the connections to basically guess as the pinout, which what I think is still a Cypress part, one of their general USB devices to interface with the USB. But Aladdin does mention that, oops, I think that should be Rainbow, does mention that they use the secure smart card controller as well. So now they have two devices on board. One is the processor to handle communication to the PC, and then they have their smart card controller to handle the secure stuff. I assume they're telling the truth. I don't see why they'd say that if they don't actually have it on board, and it's probably in the epoxy somewhere. But what you could do is maybe specific attacks against the smart card processor, or you could monitor the I/O pins to determine the interface between memory, if there is any, and that processor. Oh, good. I do have pictures. So let's see. This version, obviously, is the one that was encapsulated. After drumming a little bit, flipping it over, here's the processor. On this side, there's this other device here, this kind of rectangular one, which I thought was an oscillator of some sort, but that could be the 2030 or that Philips part. It turns out, though, that I had received a little while earlier a non-encapsulated version of the iKey 2000 back when we released the other advisory, and I didn't really think anything of it until I took a look at this new one. So what I did is took apart the other one, and there was no epoxy on it, so I could easily open it and kind of compare the features between the two. Now they've changed a little bit, but in general you still have your 24-pin SOIC here. Here's your oscillator, which I guess is that one. And then you have this other chip-on-board device, which now we know most likely is that Philips device. So, you know, having an older device, we get lucky because even though they've increased security here, we can still use this one to probe and find attacks and then apply that to the newer device. So that was kind of interesting. The other device we had was the Authenix iKey, and that was a sealed plastic housing, which is something that we had recommended from earlier, is to make the device harder to open. I knew in this case that there would be no way to open the device in a non-destructive manner, and I didn't really care because I just wanted to get to the circuitry for this talk. So I just used a Dremel tool with a standard cutting bit on it and just cut the hell out of it. And ended up with something that looks like this, which is pretty sloppy, and I'd almost cut my fingers off. But the board ended up here, and the device was here earlier, so maybe someone's looking at it or something. But this is what it looks like. Basically, you have once you get through the sealed housing, the board's totally unprotected. So once again, it's easy to kind of probe at stuff. We figured there's a chip-on-board device with a 48 megahertz oscillator, which is right next to it, and probably a voltage regulator, I think. So all the goodies are going on inside of here. Authenix does claim that there's 16K of flash on board, so now we know the memory's in here. And this would basically be our target for any sort of attacks. And in this case, what I do is some sort of die-level attack, analyze the die, see where things are located on the die, use a scanning electron microscope to retrieve data, which is a talk for another day. The user password is 6 to 63 ASCII characters stored in that same memory. So what I mentioned here is remove the epoxy and analyze the die. It's advanced, but it's extremely likely and not that hard with access to the right equipment.
So there's no crypto feature on this one?
Is there a crypto feature on? Is there a crypto feature on this one? Not that I know of, and not that I saw in the data sheets. There could be, though. And that would be something like ask one of their engineers and see what they say about it. But I don't remember them actually mentioning specifically, you know, like Rainbow said, we use the Philips smart card processor. I don't remember these guys actually stating anything like that. Any questions on USB tokens or anything before we do iButton? Question?
So for the USB token that doesn't have crypto features, does that automatically mean that on the bus we'll see unencrypted traffic?
For the USB tokens that don't have crypto features, does that automatically mean that what we see on the bus is in the clear? Yes. The thing is, for most of the crypto devices that are using, most of the USB devices that are using crypto will do all the crypto functionality on key and then transmit, I guess, known information out, public information out, but that might not necessarily be true. Like if you're trying to retrieve information from the device, yeah, it's probably, you'll be able to sniff it that way. But I assume that those areas are going to be protected with the password, so you won't be able to retrieve anything over the USB bus that's useful unless you know, unless you can get it to spit it out somehow, which would be using the password.
And then we replay.
Yeah. there another question back there?
Yeah, do you see a pathway at all to how you go about hacking into a crypto version of this thing?
Do I see a pathway on how I'd go about hacking into a crypto version? The first thing that comes to mind is die analysis, which would be, in most cases, it's going to be a destructive type of attack where I have to get through the epoxy, image the die. The thing is that a lot of the die analysis attacks, which I'd remove the epoxy using some fuming nitric acid and some other decapsulation tools which exist commercially, the device would still function after that. So it's theoretical that if somebody, if you had a weekend or something to attack the device as opposed to 30 minutes for a lunchtime attack, you could do the die analysis, maybe even just put some epoxy back on top and put it back together, unless it's a sealed type of housing. Or clone it. Cloning might be harder because depending on how the gates and stuff are set up on the die, you might not be able to reprogram what that data is. For the most part, just retrieving data, that's the way to do it. And I don't know if, I'm pretty sure Philips probably has some response or at least protection mechanisms against doing that. I don't know what. They might have layers of die so it makes it harder. I'm not sure, but that's probably the way to go. Okay, so iButton stuff. This is a totally different change of mindset here. Dallas Semiconductor, which is a semiconductor company, obviously, is now part of another semiconductor company called Maxim. They make something called the iButton, which look like these and look like these, which are small. You can come up afterwards and take a look. They're just another form of authentication token, but these are used mostly to replace barcodes, RFID tags, mag stripes, and other sorts of tracking types of things. They have a bunch of different families of devices. Some are just data storage, some are crypto, some can actually execute Java code, which is this Java ring here and also this Java ring here. It has the Java logo on it, and it's the digital decoder ring, they call it. So you can run all sorts of Java apps on here, and it's really cool. And then you just have temperature sensors and whatever. A lot of applications for these. It turns out that, I don't know if I mentioned this later, that the US Postal Service uses iButtons in every single one of their blue mailboxes to track the movements of the letter carriers and to see how efficient they are in how the mail flows. Because each device has a unique 64-bit ID that's not a secret on each device. It's internally, and it's also written directly on the device here. So it's not secret, and it shouldn't be treated that way, but it is useful for tracking. The tokens interface with the PC using a one-wire interface, it's called, even though it's actually a two-wire interface, which is clock and data and then ground. Totally different than any other interface I've ever seen, and it's really cool. It's parasitically powered, meaning most of these iButton devices don't have a battery in them. They'll get their power through the clock and data line when it's connected. And here are the speeds. 16 kilobits is the standard speed, and then 142 kilobits for the overdrive. But I'm not sure all of the devices support the overdrive. So there's tons of different types of iButton devices, and the one I went for, I didn't want to work on the Java device because they had claimed all sorts of various crypto security stuff on it, and apparently they do have a bunch of tamper mechanisms where on the Java device, if you try to open it to get access to the stuff, it will zeroize memory and erase critical areas and stuff like that, and that seemed a little too complex. So I went for the next type of security button, which they had was called the 1991 Multikey, and that was something where that they had claimed that the device was secure, and what it was is basically there's just about 1,000 bits of non-volatile memory split into 3 different sub-key areas. Each one was 48 bytes, so it's not really a lot of data. You're not going to store a ton of stuff there, but if it's used for some sort of access control or something like that, it's good. Each sub-key area has an independent 8-byte password, so it basically 3 different containers in there. Only the correct password for each sub-key area will return the correct 48 bytes of data. This specific device is used for cashless transactions like financial type of stuff. Parking meters are common in Europe and also public transportation. So it turns out that the marketing literature, actually, so let me say this. The incorrect password, when you enter the correct password, you'll get your 48 bytes of data. When you enter an incorrect password, you're supposed to get 48 bytes of random data back, and that's their security mechanism. So you can't do so an attacker won't know if they have good or bad data at that point. In their marketing literature, which is located here, and it's actually still there after all these years, says the false passwords written to the DS1991 will invoke a random number generator, which eliminates attempts to break security by pattern association. Reading this gave me the idea of trying pattern association. And it turns out that random data is not random at all, and you can determine if you have good data by doing password association. So I thank the marketing guys. What it turns out is in this attack, instead of trying to guess the password, we compare what the device returns for the 48 bytes against what we think the device would return for a bad password. If it returns other data, then we know we have a good password. So it's kind of the reverse thinking. So based on the input password in a 12K constant block, which is constant for all devices, and that's something that I'd reverse engineered, is basically just sending all various combinations of 8-byte passwords and seeing how it responds. There are details of that in one of my papers and also on the next slide. So we've pre-computed the 48-byte return value that we'd expect for the incorrect password, as I mentioned. If it does not match, then we have the correct password and subkey. And so what we end up doing is a dictionary type of attack where we just have a huge dictionary list and try to send each password and see what happens. So the way we initially found that there was some problems here is that there's something called the iButton viewer, which is part of some iButton SDK stuff that's available on their website. Shows that we figured out that the random response is based on the input password. So it was somehow correlated between what we enter and what data we get back, which is exactly what the marketing team claimed wouldn't happen. Is it constant? The random data is constant for each password, not for each. It's for each password.
So if I use the same password over and over again, I get the same.
Yeah, if you use the same password, the same incorrect password over and over again, you'll get the same incorrect random string back each time. And that's the same constant for all devices. So as you'll see, even though it might not make sense to do brute force on just one particular device, if these things are deployed in whatever European country for parking meters, you just pick up 50 of them and just do a distributed attack to figure out what sort of passwords they're using to protect that information, and then you can write your own information back in. So this is the iButton viewer, and it's a little hard to see. There's a scratchpad area that's just a public data area that's to store public data. Then you have your secure subkey areas here, and with your passwords, yeah, you see here there's two different subkeys. I have entered hello, and both times it responds with the same block of crap. And then this one down here, I just have an unprotected area. So basically, for any given character, which is going to be 256 possibilities for a byte, you get this unique 48-byte response. So what I did is just created an application to set each single byte password and then see what it came back with, so that I have 256 possibilities for each byte. And then it was just trial and error to figure out how the rest of it was figured out. And lucky for me, which I look at this now and can't believe that I actually figured it out, it's just a bunch of XORs against a gigantic constant block. So using some of the, iButton had released a bunch of SDK tools for you to work with these devices, and that just crafted up a little program to do it. So here's a little algorithm. It just goes through each byte and does some stuff. And here's a better example of it. So this is what we have here. A is the password that we enter. B is the process of stuff. And then C is the random response that it gives back for that password, if it's not the correct password, which basically just takes each byte, XORs it, or each byte. These are each of the responses that I'd recorded from each of the bytes. So that's why for the spaces down here, they're all blank, or they're all the same. And then each of these are kind of XORed based on the first byte isn't XORed at all. The second one is the first string, and then this string shifted over once and XORed. And you kind of see how these are kind of shifted over and just all XORed together. So what I have in this case is another demo called DS1991, and I wasn't feeling very marketing-ish when I came up with that name, which basically just looks on the default COM port for the device. You feed in a dictionary file. It will calculate the expected response, reads the subkey area, compares it, and if it's incorrect, it will go to the next password. If it's correct, it will display the subkey area. And let's see. Oh, I want to show you this afterwards. This is what it looks like. Search for the device, show you the unique ID, hash marks for every 100 attempts, and then it will display the password and then display the subkey data. So we can do. So here we actually, let me see. Our Word file here is just a repeating of stuff. I think the actual password is hello, so I stuck it at the bottom, but I wanted to make it long enough so you could see that how fast it actually goes, or how slow, I guess. So what we do is just do our DS1991 and feed in words. And in this case, it says it can't be found, which is right, because I haven't plugged it in.
How long is the file?
Sorry?
How long is that word?
How long is the Word file? 639 bytes. It's not big. My big Word file is 14 megs, but that might take a little while. I could actually let it run while we're doing the rest of the talk.
I was just curious how long you force.
I don't know if I have timing in here. I might have timing in my paper, but it's not instantaneous. I mean, it's serial, so it does take some time, and it wouldn't be feasible to brute force the entire thing. So what I have here is just a serial interface to the device, which I purchased from the iButton website. Plug in my iButton, and now what we have is, ignore this again, searching for the DS1991, and then it has my unique ID, and then, oh, okay, there's my password. It's you. And there's my subkey data here, which is secret information. It just dumps it out. And another way we can look at this is, you get to see all my wheres now, but I'm going to try to. You guys catch all that? So this is the iButton viewer that comes free from Maxim or Dallas Semiconductor. And right now it sees two devices on the bus, on the one-wire bus. One of them is my interface, and then the other one is the 1991. So see, the 1982 is the interface, and it has a little bit of storage in it. And then if I scroll up, it says DS1991, non-volatile memory, scratch pad, whatever. And then we click here for the viewer. Yeah, secure memory cannot be deciphered without matching 64-bit password compatible with all of the standard calls. So we click on the viewer. Oh, this is impossible to see. But basically it comes up and says, here's our scratch pad, and here's all the data. So if we go to subkey 1 and just type in like hello, it's going to display that same string that we saw earlier. If we type you, then it displays our secret information here. So we're basically emulating enough of this to just brute force all that, or do the encode and compare type of thing. So recommendations, if you are using these devices, is employ hard to guess passwords. Obviously, don't use dictionary words, mix up or lowercase, add numbers, all the stuff that hopefully wouldn't end up in a Word file. If you can, use additional encryption of the password at the application level. So what you have stored on the device would at least make it even harder for the password to guess if you're using, a random set of 8-byte values, or 8 byte value, yeah, 8-byte values. Don't use the constant subkey password between all the devices in the infrastructure, which I'm pretty sure is common for a lot of these financial things, because otherwise the key management is just a pain. And it's impossible for the reader application to know all of the different passwords for everything. It's just infeasible. So from an attack point of view, you do a distributed attack, you figure out how that's stored. Basically, the entire implementation is screwed at that point because the company is going to have to recall all of these and change all of the passwords.
So they don't even use some sort of mechanism that compares it against like unique ID. Every device is the same algorithm.
Yeah, they don't even use any mechanism to compare it somehow with the unique ID as well. It's just the same block for every device. If they did that, it wouldn't really, it might not even matter because the unique ID is still known publicly. So that would be the same thing, as it might just be a matter of time for someone to figure out how they incorporate using the unique ID back into it. For the devices, though, I'm pretty sure that it's hard, as opposed to changing MAC addresses and doing whatever. It's hard to change the unique ID of these devices without physically getting access to the die, and in some cases, it's not really possible. I've never actually opened one of these up myself, but maybe I should when I get back. So, any other questions about iButton stuff before we do conclusions? Do they send the password clear over the wire? The password for the who said yes? He says yes. Do they send the password, you mean as far as I'm sending the yeah, I'm sending the password in the clear to it. And it's doing its computation and sending the random thing back. Yeah. Right, so if somebody created a little man in the middle type of attack where you just create a false looking reader and somebody thinks they're paying for their parking meter, get stuff that way too.
But for this, you don't need to access the tablet, you just need to access the reader. So if the barcode has a reader, you can create a tablet emulator and then read the passwords from the reader.
Sorry, say that again.
The reader is things that sends the passwords, not the tablet itself. So
The reader sends the reader or the PC will send the password to it.
So you just need an emulator of the tablet. This is the same serial number. And you will get the password from the reader.
Create your own iButton.
Yeah, create your own iButton. Right, if you know what data it's actually using. Yeah, right. Yeah, you could create your own iButton that would emulate whatever you need to over the one-wire interface too, which would be kind of fun. So conclusions for kind of both of the authentication tokens is securely designing hardware is a hard problem. Obviously, research has been going on for decades, and it's not going to get any better. The devices that we looked at, they're older, but they have common sorts of problems with the external memory, with the XOR type of stuff. Encoding is not encryption. Security through obscurity doesn't work. Just hiding things doesn't work, obviously. For all three of the devices, we can access private data from the devices without legitimate credentials. And the only thing I can really say that might be useful is be aware of the physical location of your device. In that case, nobody will be able to attack it if you have it with you at all times. If you leave it for a second, if you have one of these older devices, you leave it somewhere, or you leave your iButton or whatever for a little while, somebody could do an attack against it. The newer devices are more difficult to attack, as you saw. It changes the attack type. So the lunchtime attack might not be likely, but someone who's dedicated enough to figure it out, it's still possible for them. One thing that we can start looking at now is any sort of improper implementation of crypto. Now that these companies are using the Philips smart card chip or using something else, even though the Philips device might not have any known security problems, the way that it's implemented to the rest of the system, there might be problems there, and that's what we'd look at. Nothing's ever 100% secure. Obviously, I say that probably every day. The only thing that we can attempt to do from a design point of view is make them sufficiently secure, and from an attack point of view, we don't really want that. And then learning from mistakes, and that's why we gave this type of talk, is to show some of the previous attacks and learn from history a little bit, see what had happened in the past and what we can do to make it better. There's a bunch of resources in the back, links to the papers and various things if you want to play around with the iButton stuff, the USB stuff, and there's some links to secure hardware papers and things like that, so to keep you busy for a while. And that's it. Any other questions?
So to what extent are these kinds of attacks being pushed out of the range of amateurs with more advanced technologies, protocols, things like that?
Sorry, say that again.
So,
Also, if you want the book or t-shirt, stay tuned.
so to what extent are these
okay.
kinds of attacks being pushed out of the range?
What extent are these sorts of attacks being pushed out of the range of a hobbyist type of thing or a curious kid? It's definitely making it harder. If somebody gets a hold of a USB token nowadays, they might look at it and say, man, I don't want to open mine up. I'm going to destroy it. But back in the day when you got them, it was okay, I'll open it up because there's no risk at all. So it does make it harder. And the threat now ends up being from people that are serious about breaking a product. I think there's a lot of potential looking at some other iButton security stuff as well, because really nobody's done it. And I contacted Dallas about this back in 2000 or 2001, and they didn't really seem to care at all, because it was like that same type of thing that we had with security product vendors, a few years ago, is they didn't care until there started, until there's a lot of problems out there, and now suddenly the security industry is a real industry. So it's only a matter of time until other people find problems. But it's kind of, I mean, they're totally fun to look at, and you can come up and take a look as well. So let's see. Oh, I should also mention right now with the, I already mentioned that. Okay. Who wants a book? Does anybody here either work at Rainbow or Aladdin or Dallas or use any of their products? 3 people, you use the products. Does anybody work there? Does anybody use one of the ones we talked about here? Yes? Which one? You use the iKey? Which version? Okay, so you get the book. And then for the t-shirt, let's see. This is for our new book. Has anybody read the hardware hacking book? No? You have? Okay, so you might be able to answer this question. What sort of piece of clothing was I wearing on the bio page? Hint, it's also in the proceedings.
T-shirt. Black t-shirt.
You don't know. Well, if you have the book, does anyone else have the book? Okay, well, you get the shirt. I was wearing a lab coat. So that's it. Thanks. Oh.